Alright, I hope right now I'm live. I hope I'm loud and clear to everyone. Kindly confirm it. So whether I'm loud and clear. So this is one of the very important topic as per the GATE's exam point of view. And so please confirm whether I'm loud and clear and everything is fine. So we'll proceed with the topic. This is a very important, as I have said, not only in the competitive exams point of view, but also when it comes to fluid mechanics, industrial mechanics, or whenever there is a fluid involved and flowing over any body. So this one play a very vital role. So as you know how it play a very vital role. Before proceeding, please, once again I am telling you, please confirm, because once I will start, then I will not look back over here. So make sure of that my voice is loud and clear. Alright, so here I can find I am loud and clear from the other side. Okay, without much delay, let's proceed to our core area or the core content, what we are going to discuss over here. So as you can see, let us first understand what is boundary layer. First, let us understand what is boundary layer. Okay, so as you can see in front of you, one figure is visible in front of you, a flat plate. Okay, a flat plate is there and flow is coming from the sand, right? The flow is coming. So when the flow is coming, of course, what is going to happen? The flow is going to move over this flat plate. This is a flat plate you have. Fine. And over this flat plate, this is going to be our leading edge and this one going to be our trailing edge. Why we are highlighting this leading edge and trailing edge? Because when the flow is going to hit the first, that is going to be our leading edge. The flow is going to pass by from the end of this flat plate is going to be our trailing edge. So what happens? We know several classifications of flow, right? We know what is ideal flow, what is real flow, and there are so many other variants of flow. But as per what this boundary layer explain, right, at no slip condition, when a real fluid, so this is one of the key point, is when there is a real fluid flow is passes over this strong boundary layer or a solid boundary layer. So whether it is a flat plate, whether it's a whether it's a airfoil, any solid boundary. So when there is a real fluid pass over a solid boundary, what happens? The fluid particle on the surface will have the same velocity. Okay, so what will happen? The fluid particle will have same velocity with whom? Velocity as that of the surface. Okay, so when the fluid is flowing over this body, so what will happen? That the particle velocity and the surface velocity is going to be same. And why? Because of only the viscosity. And when this happens, this is known as a no slip condition. You should understand what is no slip condition. So in your numericals or some other part, you should know what is this no slip condition. And you see here, when the flow is occurring, there is some dotted line, right? There is some dotted line. Free stream velocity u is coming and the surface velocity some other velocity. So both has to be same. So we say, what is the condition of boundary? That is a small u surface velocity has to be 0.99 times of the speed of the free stream. Okay, so this is a condition of the boundary condition, and when it is gonna satisfy, when there is a no slip condition. Alright, so when there is a no slip condition. Okay, now there are certain conditions. What if the boundary is stationary? There is some understanding. What if this flat plate or the solid boundary is fixed? So what will happen on that case? That free stream velocity is going to be 0. So if you see close to the flat plate, what is happening? The velocity, whatever might be the velocity, is going to be 0. Why? Because here the shear stress is very, very high. And how I am telling here, mathematically I am defining the shear stress as tau. Okay, shear stress as tau. You might be remembering the Newtonian's law of viscosity. It says that the tau is directly proportional to this du by dy, right? And how this came, du by dy? That is that a change, what does this mean? Is a change of velocity with respect to a change of thickness. And what is this thickness? Is here this y is the this one. This is the y direction. This is the y direction. And what is this y? Y is the boundary layer thickness. Y is this vertical one, is a boundary layer thickness, and this x that is mentioned, the critical, that I will tell you the later part. And this becomes your the dimension of your plate, and y is the boundary layer thickness, or we can say y is nothing but del of x. Del of x is nothing but the boundary layer. And what is this boundary layer? It's a very thin, or you can say it's an imaginary layer. Okay, this y equals to del of x. This is basically a thin or a imaginary layer of a flow on creating a boundary within a velocity which is varies between 0 to some value of velocity, until what happens? Until the fluid particle of the same velocity as that of the surface velocity. So this is a basic definition of the boundary layer. Alright, so here I have given a basic definition. So a boundary layer is basically a thin layer of viscous fluid close to the surface of the wall in contact with a moving stream in which the flow velocity varies from 0 to the wall, or whatever the velocity v, up to ve. Now it varies whether you write ve or v infinity. So that basically it shows the v or u infinity refers to a free stream velocity. And if you ask what is free stream velocity, there is a flat plate or a solid boundary. This is a solid boundary, and solid boundary can be anything. It can be airfoil, it can be a flat plate, it can be a surface of an aircraft, anything. So when the fluid flow is moving over this solid boundary, that is first when it is coming and hitting it, as you can see, it is defined with a violet color, or I am highlighting, overlapping with a red color. You can see that is a u infinity. But what happens when it hits close to the ground? It gets 0. See this, gradually 0, then again gradually increasing, gradually increasing, and until it became same, this C from this line to this line, it almost a straight line. So what is this line path? The small u, if I have to find the velocity of this particular arrow, it is 0.99 times of this velocity. So this is the growth of a boundary layer at this point from the leading edge. This is the x1. Now if I have to find this particular point, this will be the value of my x2. At this x2, what we can find? The boundary layer of this is different. That is del of x2 is different. because here we have to see what is the height of it. So this height and this height are both are different. And why it makes different? Because of the frictional effect, because of the viscosity and this x factor and the x factor. And in between this transaction between the x1 and x2, there might be the flow pattern might also get changed. That can convert from laminar to transient or transient to turbulent, anything. So here again the boundary layer concept play a very vital role when it comes to a Reynolds number. Okay, so make sure of that till this part, whether the definition of boundary layer is clear or not. So whether the definition of boundary layer is created or clear or not. So if you want, let me recap it once again, or let me rephrase the concept. So if you have a flat plate with it and a flow is a upstream flow, okay, upstream flow is coming, which is defined as u infinity. So what will happen when the flow is coming and hitting to the leading edge? What will happen if the u infinity is there close to the surface? The u infinity value at that particular close is going to be 0. Now why it is going to be 0? Because of its frictional effect, because of its shear stress. The shear stress is going to be 0. So going to be very high, going to be very high, so that the velocity is no longer moving from it. Now gradually what happens, this layer is unable to hit the ground, okay, 0. Now next layer, next set of layer is coming. So again, if the magnitude of this is, imagine 9.01 meter per second. So here in the close to the surface, okay, if I magnify this zone in a larger scale, this is my flat plate, okay, I am creating a graph scale, right? So what happens in a very minute scale, what happens, the flow used to be something like that. It's going to be, we call as a parabolic in nature, okay. Okay, so what is this pattern? That means close to the surface, this is a surface, okay, close to the surface, and this point what is happening, velocity is 0. In next layer, velocity is somewhat like maybe 1. Now next layer it's 2 meter per second, next layer is 3 meter per second. I am magnifying the scale, okay, when the flow is moving over the surface. Another some height, maybe each of 1 mm, 2 mm, 3 mm, 4 mm of flow, I can find it is of 4 meter per second. Here it is 5, then 6, then 7. Gradually when the height is around 8 mm, right? The 8 mm, what happens, what I can find at this stage, my speed is what I have obtained in the ahead of this, okay. So here it is a 9.01 meter per second, and it took around 8 mm, it was around 8 mm to reach with the same surface with the fluid flow. So this growth of this height is known as a boundary layer, which is denoted by, mathematically denoted by del of x, okay. Why we are giving x, I will tell you a later part, because this is a leading edge, okay. This portion is a leading edge. From some distance from the leading edge is the value of x. So I am not taking directly from the leading edge, I am taking some distance away from the leading edge. So that's why I am giving as a del of x, okay. So del of x, what is the value? So now we got at some 8 mm height, that is our boundary layer growth, is giving this equivalent value what was in the upstream. This concept that what is a growth or what is a y value or what is a height, okay, to make an equivalence whether u is has to be almost close to the u infinity, and which gives not accurate, there is a 1% error, that is u equals to 0.99. that is, this is the value of u, this is u infinity. Okay, so u is almost close to 0.99 times of u infinity. Okay, when this condition satisfied, this is called as a boundary layer, and the height that it needs to create it or create a growth of it, this is about the boundary layer thickness. Okay, this is what is known as a boundary layer thickness. It is not this is just a rough value I have shown or explained it. Okay, now what it says that when it exactly becomes u is equals to u infinity or that 1% error, this is a condition is applicable only theoretically, which is also known as a no slip condition. Okay, these concepts are very important when you are going to go later part of this session. You are going to do a numericals also, and this also satisfies Newtonian's law of viscosity, that is tau is directly proportional to du by dy. What is du by dy? That is the same thing. Okay, so this one is our y and this is our u. Okay, there is a change. If I have to find this particular element, in this particular element, that is a change of my velocity with respect to change in thickness, how it is going to vary my tau, that is a shear stress. And to ignore this directly proportional, we get an equals to, that is a mu, that is a dynamic viscosity, du by dy. Okay, so again this one, that is Newtonian law of viscosity, play a very vital role when it comes to an boundary layer thickness concept. Okay, so this is a very important and also one of the when it comes to competitive exam point of view. Okay, now what I have explained here, this x1 and x2, as the flow pattern changes, so the x2 will also get varied, right? That is the understanding. Now here a slight of bit of history. Who has created this concept is derived by one of the famous scientists. You should know the Prandtl. It has been developed in the 1904. Okay, this concept has been developed, and yes, this is primarily and directly related with the Reynolds number, that is Re. You should know how this Re varies and how it's important. You should also know this formula, that is R equals to rho Vd by mu. So as you know, this one play a very vital role. In previous session we have also seen the minor losses, like how to find the F factor, that is a coefficient of friction, where it also required the understanding of Reynolds number also. So this one and this one has quite a good interconnections between them, right? So let me just skip this other theoretical part and moving to the core of it. Now here you should know some of the important characteristics of boundary layer, some of the very important. So the first one, the first understanding is that near leading edge. So what is going to happen in the near leading edge always? So some of the conceptual question can come up on this. So near leading edge, always the boundary, so in short we can write boundary layer as B dot L. Boundary layer is going to be a laminar always. Okay, so there might be, why I am giving you this, there might be question, this particular value is near to the boundary layer. Okay, so you should understand that if in order to find the Reynolds number, you don't have the viscosity or you don't have any other certain parameters. So in that case you can apply this concept and obtain what is the value. Okay, Now, second concept, important concept, that is a boundary layer thickness increases as it increases the distance from the leading edge. Okay, so what you can understand from this figure, if this is a distance from this leading edge is x1 and this one from the leading edge is x2, right? This is our boundary layer of del 1, this one is our del of 2. So in this case what will happen, of course the del 2 is greater than del 1 if the x2 is greater than x1. This is a concept. Okay, so as it is increasing the length from this leading edge, so what will happen, the increase of boundary layer thickness will also increase it. So they are basically, you can say they are directly proportional, and in future we'll also see how this particular thing is mathematically related. Next important point that we are going to see is that next important point that how this boundary layer is related with the velocity. Now when the velocity, or you mean to say here is that how it is relating with the upstream velocity and affecting the rest of the parameters. So understand they are indirectly proportional. These are the hinting points. If this boundary layer thickness is increasing, so of course what it has to be, that in that case the velocity, or I can say the upstream velocity, that is a u infinity, has to decrease. Or I can rephrase in other way, that if the boundary layer is decreasing, so the upstream velocity will increase. So vice versa. Okay, they have a vice versa connection, right? Now the fourth one is that how this is related with the kinematic viscosity. Okay, now as I have said, this del has a direct connection with the Reynolds number, has a connection, direct connection. So I have not said whether it's a directly proportional or indirectly proportional. Both the statements are different. I have said they are connected. Okay, so now you know what do you mean by Reynolds number. Here I am going to show you with the kinematic viscosity. There are some questions they are asking in terms of kinematic viscosity. So as I have written the formula, rho v d by mu. So this formula can also be rephrased as v d by nu, and this nu is the kinematic viscosity. So here what is the understanding from this? If the boundary layer in thickness is increasing, right, the kinematic viscosity, that is a nu, which unit is meter square per second, is also going to increase, right? So can I say with this that how it is relating with the Reynolds number? Of course it is. If boundary layer thickness is increasing, the Reynolds number has to decrease. Or I can say if the Reynolds number is low, then the boundary layer thickness will increase it, right? Okay, so likewise there are ways to predict it. Now what's the value of the, at what condition? Now you should know one more important part, at what condition this boundary layer thickness will be a laminar. So understand the two different things, whether it's a pipe or it's a flat plate. The understanding of laminar flow is slightly differ with the values. So in case of flat plate or a boundary layer, if the R value is less than 5 into 10 power 5, then this one is referred as an laminar condition. Whereas if the Reynolds number is greater than 5 into 10 power 5, then it is comes under the turbulent flow. Okay, so here whatever the value, when you substitute and check this, if it is less than 5 into 10 power 5, in fact even you get 1 into 10 power 5, still it is comes under your laminar flow. Understand the condition whether you are finding the laminar flow for an boundary layer or a flat plate, or for a pipe. This is an important point to take away. Right. Before proceeding with the mathematical forms, right, so let us first understand and discuss that how actually the boundary layer occurs and how actually the flow separation occurs. So boundary layer, as you know, as you are quite well versed with both the objects, I can say. Okay, one is object 1, this is object 2. Object 1, we have a very streamlined pattern, or we can say it is also an airfoil, right? It is also an airfoil. Whereas object 2, it is a bluff or a blunt body, right? So this is a airfoil, this is a cylinder or a bluff body. So as you can see the flow pattern, and this airfoil is inclined at some angle. It is have some angle of attack. It is having some angle of attack. And what you can find when the flow is coming at some point, as of in this figure is given, at some point what is happening, the flow started to separate from this point. The flow has started to separate from this point. Same, look for the object 2. After this the flow has started to separate. See, there is a word called flow separation. Okay, there is a flow separation. Fine. Now we must understand how being an aerospace engineer, you are well versed with the concept called drag. Now let's understand how this drag actually play a very major role in understanding the fluid mechanics and the flow pattern. So drag basically or majorly can be split in two ways, right? One is a pressure drag, okay, and second one is a skin friction drag. Okay, so when if the surface area is high, if the surface area is high, of course the skin friction will be more, right? If the body is blunt, so the pressure drag is going to be more. Okay, now these are very easy concept. So here what I have written in a simple way, the pressure drag I have written in a short form is an PD, and skin friction as a SF, right? Now if I have to compare between two different objects that has been presented over here, that is the airfoil and cylinder or a blunt body, so what you can predict from here? So that is a skin friction has a this streamline or as a airfoil will create a measure of the skin friction drag, because the surface area of this is more, right, as compared with the cylinder. You agree with me? So there is a comparison that for airfoil the skin friction drag is going to be more as compared with the blunt body, whereas the blunt body or the bluff body will have a measure of the pressure drag as compared with the streamline. Okay, now how it actually helps to occur a flow separation. So what do you mean by flow separation? Is a point at which the flow or a fluid started to separate. Now what is separate? It is no longer creating an attached flow. Now let's give you a very basic example. All of you are well versed with the airfoil, and now I have an airfoil with me. Let me redraw this airfoil once again. This is a chord line, this is a leading edge, okay, and this is a trailing edge. Okay, this is a trailing edge and this is a leading edge. Fine. Now what I am doing, now I am creating a flow to be flow over this particular airfoil. This is an airfoil I have sketched. Now At this particular point, what is happening? The flow will be completely attached with the surface and leave behind this trailing edge. But whereas, as I am increasing the angle of attack, now this is a 0 angle of attack that I have made it. But imagine this is of 25 degree of angle of attack, this one. So what is happening from this? The flow is no longer attaching, it is splitting from this end, right? So after this, when the flow is moving, so rest of the flow, what is happening? They are haphazardly moving within the surface of this, and what they are creating? They are creating a chaos at this particular region of the surface, So what it happens, as it is haphazardly, the flow is moving all around this. The fluids are haphazardly moving and creating a chaos. So they are no longer the fluids at laminar, they have converted into a turbulent, they have created as a turbulent flow, or they have created a wake formation. Right? So what is happening in this case? They are creating a wake formation. So there is this, because of formation of this wake formation, it creates a high pressure zone. Just a second. Yeah, it creates a, in this particular zone, let me change the color. In this particular zone, right, what is happening? It creating a high pressure zone. So most of the time you are quite aware of it. We have an airfoil where we need to increase the angle, because here bottom we should give an high pressure and top we should be a low pressure. So then only the lift force will be creating, isn't it? And that's how the entire vehicle will produce a lift. But if it creates a reverse, that upper zone, this particular zone, we are having a high pressure, and bottom as compared with the bottom zone. So what will happen? There will be a measure of the downward force will try to create. So instead of going the upward direction on the lift force in this direction, it will try to move to the downward direction. So it is degrading the lift. So this play a very, very vital role. So we must understand that what should be the right angle, so the flight no longer creates such kind of flow separation, and we must ignore to reach till the flow separation zone, right? And the reason being is, this is the reason that why we need to avoid this flow separation zone, right? Now here already I have explained that how this actually play a very vital role. Let me once again give you a brief of it. So when it comes to a boundary layer, the Newtonian law of viscosity play a vital role, and when means the viscosity, that is tau, is directly proportional to mu du by dy. So du by dy is also can be defined as just a second. This also be depend as a shear strain, right, which depends on the shear strain. And what are the shear strain is also further can be rephrased, that is a rate of shear deformation, rate of shear deformation. And how these things are dependent on the nature of flow. And what do you mean by nature of flow? Whether it's a laminar, whether it's a transient, whether it's a turbulent, right? Now imagine there is a figure given to you, and so can you find what will be the du by dy? Yes, so that is nothing by the slope, that is a gradient we call, that is tan theta. We can find what is the angle of this. If I create a straight line from here, and there is an angle subtended theta, this particular change of this x direction we can take as dx, and change in y direction is dy, right? This is our dx is nothing but a du, right? So du by dy dy by dx, that is nothing but dy by d of x is our u, is of tan theta. So theta is tan inverse of dy by du. So you can find what is the slope. It's nothing but the reverse of this fact. Okay. So similarly you can find for different flow regimes, right? So there are certain theoretical part. What are the how you can measure the viscosity? There is a viscometers and rheometers. How you can find it? Yeah, one more important concept is the fluidity. Fluidity is a reciprocal of viscosity. These are theoretical part you can understand. Yeah. So as we were discussing this, that du by dy is nothing but the inverse of this law, and yes, okay. Simultaneously, let's understand this particular part also. So let's relate with this figure that is shown in A, B and C. Okay. First we'll look into this figure, the first one. Then we will simultaneously look into that how it is affecting the pressure, as I have early mentioned it about the pressure. Now let's take an airfoil or any object, how it is actually create a major impact. So in this A stage, B stage and C stage, we'll see how drastically the flow pattern changes and how drastically the pressure fluctuates and different stages of this when the flow is started to separate. Now A is a point in this particular stage is that there is no flow separation is taking place. There is an object. The flow as usual near close to the surface, the tau has to be 0, and it has its own boundary layer thickness, that is a del or del of x, where this particular is 0.99 times of u infinity. It perfectly follows all the non-slip conditions. Moving further, in this stage B, the stage B states that it's begin to separate, or we can say verge to flow separation. That means that flow is initiating to separate it. So you can find the difference between stage A and B. In the stage A, this is again stage A with the pressure stage B. So when it started or verge to flow separation, so what it is happening during this phase, what is happening, the pressure is increasing from point A to for the phase or the case A to case B. So what is happening, P2 is getting greater to P1. So if I need to find how it is affecting the change in pressure with respect to change in distance, that means the pressure gradient we call as a pressure gradient. We call as a pressure gradient. The pressure gradient is negative, which is advisable when it is transiting from the phase A to phase B. Yes, the P2 is increasing, but yes, still it is in a phase where dP by dx is negative. But you see, when the flow is further transiting from B to C, so B is started to verge to flow separation. Okay, verge to flow separation. So flow separation and initiated and implemented. C is already implemented. So whenever there is a implementation, that means the flow is going haphazardly, that is flow is undergoing a reverse flow. So no longer it is going a positive flow on this direction, it is going the reverse direction, then coming in this way. So this is what but the original flow is on this direction, and see from the ground it is getting in the opposite direction, then after certain height it is moving to its respective thing. So whenever there is a reverse flow or turbulency or already initiated to flow separation, so that shows it creates an adverse pressure gradient, and what it says that the increase in pressure as it is increasing the as it is increasing the surface, or we can say the change in length. Okay. So for an example, if I have to see in this particular figure, right? What you can see, at this stage everything is normal. At this point it has been initiated to flow separation. Furthermore, if I have to find somewhere on this point, this is a C point, so already the flow is going reverse. So as I am gradually moving to any other point over here near the trailing edge or in between the C2 trailing edge, already this has been, the flow has been expanded drastically, right? So it has already created a flow, the pressure has been drastically increases. So this particular symptoms is known as a adverse pressure gradient, and basically what it is known as a stalling or imbalance. And because of stalling, the flight can be imbalanced, there can be a structural damage, and it can lose its stability and control of the flight. Okay, so these are the major understanding that you can see, and each and every phases, that how before flow separation or the condition of laminar flow, how this change in pressure with respect to distance, how it is affecting. And furthermore, as it is increasing the distance and initiating the flow separation point, and gradually it initiates the reverse flow and the pattern, how drastically it is varying, and how it is creating an adverse pressure gradient, right? And what are the different conditions, right? Okay, so as of today I will just wind up the session over here, because before proceeding we have few more important topics. So into this we'll come and solve some numericals in the later part based on the same condition. So I will request everyone, so please go through this particular topic today, and tomorrow we will furthermore proceed from this particular layer, because this is very, very important. I really doubt that how much you have really understood this particular topic. Okay, so first thing is first you go through this particular topic. If you have any questions, you can drop in the chat box. Alright, you can drop in the chat box, and make sure of that, refer the textbook, or if you have any doubt right now, you can drop in the chat box also. I can discuss that, because once you understand that, then you will understand the rest of the other part, and you will also able to find and identify the rest of the thing. So next class we will also study how it is going to affect with the temperature and the velocity, right? So first thing is that you please do refer this first boundary layer, the mechanism, the flow separation, and this particular area at different what do you mean by, you know, we have attached flow condition, what is the scenario, whether the du by dy has to be positive, worst flow separation, the du by dy has to be 0, and already separated, the du by dy is going to be negative. So how it is going to negative, how how it is affecting the pressure difference or the pressure gradient, that also you should keep in mind. Okay, so everything, this figure will explain everything. This particular figure will explain you each and everything. So first give some time for this, understand this particular fact, alright, and then we'll proceed for the next. Okay, so meanwhile I will give you some time, so if you have any questions, so we are ready to take it further. So we will continue in the next class. So do you have any question? I believe you don't have any questions, so we are winding up the session over here. So thank you everyone. I hope you have learned this very, very important topic, and you can expect some questions out from here, and in future you need to understand the concept on basis of this, right? So thank you everyone. See you soon in the next class, right? So take care. We are winding up the session over here.